Good morning, everyone. Let's finish our notes from yesterday, and then we'll move into the second part of chapter 4, which is with average value theorem. Okay. So let me do a little bit of recap on what we covered on the first page, and then we'll finish the rest of the second page that we didn't get to. And then we have two topics today: average value theorem and second theorem of calculus. And we'll, if we have time at the end, we'll do some practice on those two concepts. Okay. So yesterday we talked about how we are kind of extending that idea of antiderivative. On the quiz, you guys were able to apply power rule, find the antiderivative, and you would say plus c, right? Because I was asking for a function. But the result of that function is going to be an area finding formula. So we learned yesterday that we're able to take that antiderivative that we found, and if there are bounds provided in the original problem, we can plug those values into this area formula, and in return, we'll get a number, and that number is corresponding with the area of this graph under the graph between the two bounds. So we went through some examples practicing that concept, right? We started the steps with imagining the bounds not being there and just pretending like it was just a problem that we were doing from the last quiz. Go through power rule, but the difference is that we're going to leave the plus c out. Okay. We have the expression, we'll leave the plus c out. I cleaned it up. And now I have my area formula, and now I'm going to involve the bounds. So now I can plug my bounds into my area formula. In return, I get a number, and that number is going to correspond to the area of this region under this curve. Okay. Now I keep saying area, but sometimes it may not be the area. It may be an area-related information, but not completely area. So we may get a negative number, and that negative number just means that we have accumulations of values below the x-axis. That's more than the accumulation of values above the x-axis. So that it's possible to get a negative value. So right now, just to understand that the depth integral gives you the accumulation of change from one bound to the next. If we want to find an area of a region, we won't talk about that formula until chapter 7. But right now, just understand that it's area related, but not quite area in some instances. Okay. Two mistakes, two big things that I see where students make mistakes with depth integrals. I'll point those out. The first is, I think it's the natural tendency, right? We see the bounds, we see the function, and we just want to go ahead and plug in. But this expression is the graph, but this is not the area formula that we need. So we have to make sure that we don't plug the bounds into the expression. This expression is not ready for the bounds yet. We got to make it go through calculus. We got to make it become its antiderivative before we can involve the bounds. So that's a big mistake I see students make. They just want to go ahead and plug it in because it just looks like a natural thing to do. So the next thing is make sure that when you plug in your upper and lower bound that you protect the lower bound with a set of parentheses. Otherwise, you may not remember to distribute the negative through. So I like to put my expression, the upper bound doesn't require a set of parentheses, but before you plug in the lower bound, just create a space with parentheses, then plug in the lower bound and make sure you have the set of terms inside parentheses, because there's a negative outside of it, and that we don't want to lose track of that negative. Okay, so we also talked about properties. We talked about how if my bounds are the same, that means I haven't moved. That means I started and ended at the same place. If I haven't moved, that means that there's no region for me to find. So that's always going to be 0. Okay. The second property that we talked about was how it may be beneficial in some instances for us to flip the bounds so that we can kind of think about the problem from left to right rather than thinking backwards. So you're always free to change the bounds, but understand that if you flip the bounds, you're changing the sign of the answer. So to maintain balance, if you want to flip the balance, make sure you balance out with a negative in front so that you're not, so whatever change you make, that you're balancing it out so that you're not changing the overall problem. The next property is we can always take a larger region and split up into the sum of smaller regions. And sometimes dividing and conquering can help. If we have a messy problem, we can kind of handle them in chunks, and that may help us solve the problem a little easier. Okay, I think we got through these examples here, but we ended with D, where we have to understand that this +3 is not just a +3 by itself. That +3 is inside the integral notation. So what we did was we thought of it as two separate problems, integral of f of x and integral of 3. The integral of f of x, we can rely on the property, the information that was given to us about the function, and just realize that we're making a substitution with a -1. But the integral 3 dx is a standalone problem. We have to go through power rule, plug in upper and lower bound, get that answer to be a 9, and then we total those two values together. 5 plus 9 equals 14. Okay, so we're going to finish up with examples 4 and 5. Let's see. So let me read example 4. It says we have the definite integral from 3 to 8 of f prime equals 10, f of 8 equals 6, and we want to find f of 3. Okay, there's the reminder that SFTC, that's just first fundamental theorem of calculus, can be used as an equation solving tool to find the value of the antiderivative at a specific point. So let me write the first theorem again. So I'll put this below. So the first theorem says that if I want to find the definite integral of f of x dx, I'm going to first transform that f of x into its antiderivative, and the formula, the theorem, represents that antiderivative as an uppercase f. And then once we have that antiderivative, we can plug in our upper and lower bounds. So this is kind of like the general formula. But we can also develop this formula for a specific instance, right? As long as there's that relationship from a function to its antiderivative, we can have different variations of it. We can go from f prime to f. We can go from f double prime to f prime. They all kind of fall under this theorem. So specifically, we have something in terms of f prime, so we can build something in terms of f prime, just basically following this general theorem. So I can say the integral of a to b of f prime, I'm going to make this turn into its antiderivative, and f prime specifically is going to turn into f of x. So my uppercase f can be represented for this equation as f of b minus f of a. All right, so I'm converting that f prime into its antiderivative, which is going to become f. And then once I have my area formula, I can involve my upper and lower bounds. So I think this is helpful because this is the form that our expression is in. Oops. So what if I just replace 3 and 8 in for a and b and just fill in everything I see with 3 and 8 for a and b? Maybe that will help me figure out what f of 3 is. So I'm just going to take this information and put it into this adapted theorem that we just have. So I have 3 to 8, so I'll put 3 in for A, I'll put 8 in for B. So f prime becomes f. I'll replace B with 8, replace A with 3. So now that we have an equation that is more specific to what we have that's given to us, we can look to make some substitutions, right? What can I replace the integral from 3 to 8 of f prime with?
F of 8 is 6.
Okay, f of 8 is 6, okay. What about this piece right here?
10.
Right, that's 10, right? Okay, so I'm going to make that substitution. So now I'm in the clear because the only information that's left is f of 3. I can solve for f of 3, and that's what the problem is asking for, right? So I'll subtract 6 from both sides. Okay. Divide both sides by -1. I can get f of 3 to be positive, so f of 3 equals -4. All right, any questions with 4? Everybody good? All right, let's go down to number 5. Number 5 says the area of each region is given. So 10, area of 10, area of 2, area of 3, find the definite integral. The only thing we have to do, we're going to be adding these numbers up, which is pretty easy. But just understand that if we're dealing with definite integral, we got to make sure that regions below the x-axis get adapted to the correct value. So anything below the x-axis, just have to make sure we got to convert this to a negative value, because we're accumulating negative values below the x-axis. The 10 and 3 will stay positive, but we should make sure that the 2 becomes negative. And now we can just total those values up. (10 minus 2 plus 3). Okay. Any questions here? All right, let's go to today's notes. Average value theorem. So this is called average value theorem, which I put in parentheses. This is the mean value theorem for integrals. So let me recap what mean value theorem is, and we kind of see a little bit of connection between that and this new theorem. So mean value theorem for derivatives is where we can guarantee a slope. So last semester we talked about how if I have 2 endpoints, and if I'm able to find the slope between those 2 endpoints, whatever that slope is, let's say that's a slope of 2, we're guaranteed to have that slope show up somewhere along the curve. As long as our graph is continuous and differentiable, no jumps, no sharp turns, and we're able to find the c-value, and we just have to make sure that the c-value falls between the interval. Okay, so we can guarantee a slope with mean value theorem. With average value theorem, it's now going to be area based. So amongst all the heights in our region, we can find that average height through this formula. And after we find that average height, we can guarantee that the graph is going to touch that, is going to cross over that average height somewhere along the region. We can guarantee that average height is going to be reached by the graph. So mean value theorem is guaranteeing a slope. Average value theorem is guaranteeing the graph is going to hit that average height somewhere along that region. Okay, so let's talk about this area here. Okay, so the area of this region, imagine this was like Play-Doh, where you're able to kind of mold the shape of this object. And if you're able to, we can always mold the shape into a rectangle that will share the same area as this region. So whatever rectangle we're able to create out of this shape, then the height of that rectangle is going to be the average value. So I'm going to go back to this idea of rectangles, and that will help us understand where this formula is coming from. Okay. So let me ask you this. What is the area formula for a rectangle? Okay, so width times height. So our average value is our average height. Okay, so let's say that we want to solve for height. How would you solve for height? How would you get height by itself within this equation?
Divide by width.
Yeah, divide by width, right? So area divided by the width equals height, right? That's a easy concept, right? We know the formula, we're just kind of rearranging it. So we're basically going to be working off of this formula. It's basically just area divided by the width. And I want to start with this idea and show where this formula is coming from. So height is the y value that I'm looking for. So I'm going to call that f of c. That's the average value. Area, we associate area with definite integrals. So I'm going to say the definite integral from a to b under f of x is my area. The bounds are highlighted as a and b, divided by the width, and the width is just the distance between my endpoints. So that's just b minus a, right? That's the width of my rectangle. Okay, so now this looks kind of messy, right? You got the integral with the b minus a below it. So what the formula is presented as, it's pulling that b minus a out in front and just writing it as a fractional coefficient in front of the integral. So just making a minor adjustment, pulling that b minus a out in front. So that's why it's 1 over b minus a, definite integral from a to b of f of x dx. So we can find the height of our rectangle by taking the area and dividing it by the width. Okay. So we're just going to spend some time practicing this formula and finding the average value. And then we're going to take the additional step to figure out where that average value is located and trying to find the x value of that order pair. Okay, so let's go to example 1. I'll put the formula here again to make it easy access. So example 1, find the average value of our function from 2 to 5, find the c value. We'll do that part B later. First thing is find average value. So we're just going to take this information and just put it into our formula. So what are our a and b values?
2 and 5.
2 and 5, yeah. So we just make our substitutions and get it ready for a specific. Okay, f of c equals 1 over b minus a, 1 over 5 minus 2. Okay, are we good so far? Yeah, I'm just making my substitutions, right? Okay, what does that 1 over 5 minus 2 clean up to be?
Oh, yeah.
1/3. Okay, so if you look, this problem is not much more difficult than what we were doing before, right? We just have to keep track of a coefficient in front, but really same process, right? We're going to pretend like the bounds are not there. We'll do the antiderivative, we'll do power rule, we'll plug in the upper and lower bound into our area formula, and then just at the end, just multiply by that 1/3. Okay, so let's practice through those steps. First things first, I'm going to just worry about power rule for this expression. I'm going to handle this portion first before I do anything with a bounds. Okay, what does x squared plus 1 turn into?
X cubed over 3.
Plus.
Plus x.
Okay. And we are going to leave the plus c out because we're dealing definite integrals, and so plus c is just going to wash out. Okay. Okay. Now I can involve the bounds. And I'm just going to put a 1/3 in front. You can multiply the 1/3 through at the beginning or in this problem, but I'm just going to wait till the end. I just want to make sure I don't lose track of that 1/3, so I'm going to just put that 1/3 there so I don't forget about it. But I'm just going to handle this area portion first, and then I'll deal with the width later. Okay, so upper bound gets plugged in first. Minus, okay, remember, protect the second region with a set of parentheses. Okay. Now the 2. Okay, we'll clean all this up, and this will be the area, involve the width at the end, and then we're going to result in a height value or average value. All right, see if we can make progress there, and we can check our answers. Feel free to use your calculators. Okay, you guys get 126 over 3? So double check to see if that is what you got.
Oh, did you multiply the 1/3?
Not yet, but yeah, but we are going to do that, right? But the 126 over 3 is the area, but then I highlighted that 1/3, we still got to take care of that 1/3, right? Area divided by the width is same thing as area times 1/3. You guys get 14? Okay, good. So that's part A. We have the average height. If we're able to take that shape of the graph and mold it into a rectangle, the height of that rectangle will be 14. Okay, any questions with part A? Okay, so now part B is we want to know where that height is located on the graph. We want to know what is the x value of that location. So we simply just involve the original function. We'll just plug 14 into the y value of the original function and then solve for x. And when we solve for x, we can get to our c value. And when we get to a c value, we've got to make sure c value lives where? Within the interval, right? Good. Okay. So my function is x squared plus 1. I'm just going to put that 14 into the y location of my function, and then just going to solve for x. So subtract 1 from both sides, take the square root. I get plus or minus square root of 13. But because I'm starting at 2 and ending at 5, I don't want anything outside of that interval. So negative root 13 is clearly outside the interval, so we only keep square root of 13. That's the only guaranteed location on the graph where we know it's going to cross over that height of 14. Okay, any questions? Okay, I'll give you guys a minute to copy that down. Okay, everybody good? All right, next page. Okay, we just got done practicing first theorem of calculus. Again, first theorem of calculus just is that area formula that we've been doing where we convert a function into its antiderivative and we plug in the upper bound, lower bound, and subtract them. So there's also this second theorem of calculus, which is going to be really helpful for us. It's kind of like a shortcut method. And what this does is highlighting the fact that a derivative and integral, if I apply a derivative and integral onto the same function, what's going to happen is my function is going to remain unchanged for the most part because I'm doing a process, but then I'm undoing it. So I'm kind of left with what I started, but with some slight adjustments. So let me just read through these notes here. So to recap, we've covered indefinite integrals, indefinite general integrals. Indefinite just means that you have an integral with no bounds, which means that your answer will be in terms of x, and then you'll end up with a plus c. But it is the area of finding formula that we're going to be using. So definite integrals is where we apply that process, but then we have to plug in our upper and lower bound, and we're going to get a number, and that number is going to correlate with our area. There's also a function where the function is the integral itself. Instead of going from a constant to a constant, we're going from a constant to a moving value of x. This seems like a complex idea, but we're going to be able to use second theorem to help us get this into something a little cleaner. Okay, but right now I just want to show that relationship between derivatives and integrals with second theorem. So yesterday I briefly kind of talked about that. So yesterday in that summary sheet, let me just pull that up real quick and we'll go through the formula. We briefly talked about how if I apply a derivative and integral onto a function, the resulting answer is still going to be largely that function. There's going to be a little bit of leftover things that we're going to be talking about, but notice that what I started with and what I ended with didn't change much, even though I applied two process. And the reason why is because they're opposite, right? They're going to kind of undo each other. So we're going to take advantage of that, meaning that we're not going to spend the time to find the integral and then turning around and find a derivative. We're just understanding that they're going to cancel each other out, and we're just going to have to make some slight adjustments, but we're not going to make a whole lot of changes to our problem. Okay, so here's our theorem. The theorem says if I find the derivative of an integral of a function, my function is not going to change much, but there's going to be some impact from these two processes. The impact is that the upper bound variable is going to end up getting lodged into the variable of my expression. So every variable in my problem, I'm going to replace with that upper bound that I see. And then the derivative is going to have an impact on that upper bound as well, meaning that I got to multiply with p prime. So my function is not going to change much. I'm not going to do a whole lot of calculus here. I just have to put that variable into my problem, and then just do a derivative of that upper bound and include that. Okay, so let me show some examples, and hopefully this will make sense. But you're going to see that this is a nice process because you're not going to have to do a whole lot of calculations, even though it looks like a big mess. So let me zoom in a little bit here. So example 2, we're going to find the derivative of a definite integral of square root of x squared of t squared plus 4. This looks like a whole lot of things to do, but these are opposing operations. So the only thing that's going to happen is we're going to plug the upper bound into the variable. So what is that going to look like? Instead of t, we're not going to replace t with what? X. So square root of x squared plus 4. And then the derivative is going to have an impact on the x, so we're going to have multiplied by times p prime. So what's x's derivative? 1. And that's it. So there's a lot of things going on here, but because they're opposite things, we're just going to basically make some slight adjustments and not go through the entire process. Oh, I forgot to mention the lower bound. The lower bound is a constant. So that constant, it does get plugged into the expression, but the derivative is just going to force that constant to be a 0. So anytime we see a constant, we can kind of ignore it because this derivative process is just going to wipe it out to be 0. Okay, all right. Any questions so far with A? Okay, let's look at part B. Again, process, we see opposing process here. We just have to make some slight adjustments with our expression. So replace t with, yeah, that's what this notation says. It just means I'm going to put my upper bound into whatever I see in my expression. Times p prime, what's my upper bound's derivative? 2x. My lower bound is the constant. We can ignore it. It'll just go away. So this is it. Okay. Any questions there? All right, part C. Same problem, right? The only difference between B and C is what?
The lower bound.
The lower bound. And we know the lower bound is going to go to 0, so we'll get the same answer, right? Square root of x squared minus 1 times 2x. Okay. Any questions A through C? All right, part D, derivative and integral, they're going to be combining on top of an expression. But what's different about the setup here? Yeah, my upper bound is a constant, my lower bound is a variable, right? It doesn't quite fit into our formula that we want to use. So can I adjust it to make it fit my formula?
You put a negative sign.
Yeah, so I can flip the bounds to make it match my rule. But if I flip the bounds, I don't want to change my overall problem, so I'm going to put a negative in front. I'm just going to put a negative with the numerator. You can put it anywhere you like, but I'm just going to put it there. Okay, so now we can go through our process. What's the first part going to look like? Mm-hmm. Yeah, but everything else stays the same, right? We're going to recopy your entire expression, just make a simple substitution. Times, yep, upper bound's derivative. Okay, any questions here? Okay, part E. Anybody still need this? Okay, part E. What do you notice is different about part E?
They're both,
Yeah, they're both variables, which means that they're both going to leave some impact in our answer. So let's talk about, there's a formula for that. If I have upper and lower bounds being both variables, I'll repeat the process twice. I'll do that process for what I did with upper bound. I'll also do the process with my lower bound, but I should have separated with a minus. So I'll do my upper bound just like how I did before. I'll repeat the process for lower bound, just put a minus in between, and then we can clean up our expression. Okay? So what would the first part look like?
2x squared plus 3 times x squared.
Wait, times,
X squared. Or 2x.
yeah, times 2x, okay. Make sure you put this in a set of parentheses so that you remember that, okay, this entire expression is going to be multiplied by 2x. So I took care of my f of p of x times p prime. My lower bound is not going to go away because it's also a variable, so I'll put a minus, and I'll do the same thing with my lower bound. My lower bound will look like what?
2x plus 3.
Times
1.
Yeah, so no impact, but I just want us to make sure we are remembering that part of the process. All right, do these steps make sense? Okay, so now let's just distribute through, combine like terms, and get down to an expression. Okay, did you guys get 4x cubed plus 4x minus 3? Okay. All right, any questions? Okay, so with the remaining time, let's just do 2 practice problems. We'll do 1 average value, just have you guys practice. I'll see how you guys do. And then we'll do a problem where we practice second theorem, okay? So just find space on a separate sheet or on your notes. I'm just pulling problems from the textbook here, so try this one here. Does anybody still need this? Okay. All right, here is the average value theorem. I'll put the formula. Oh, let me zoom out. So just like the one that we did, or same steps as what we did on that first page. So use that as a model to kind of help you through the steps. I'll see how you guys do, and then we can check our answers. Sure, you do power rule before you do anything with the balance. And don't forget about that coefficient, that fraction out in front. Make sure you end up involving that as part of your answer. Feel free to use your calculators. So this is what I have right before I plug before I apply my power rule, right? So I replaced my a and b with 2 and -2. I cleaned up my fraction, but now I'm going to focus on the 4 minus x squared, right? Don't do anything with the bounds. Convert that 4 minus x squared into its antiderivative, and then you can do a half bracket, and then you can plug in the 2 and -2. I'm just choosing to wait until the very end to handle and to include that 1/4. So I'm just copying down 1/4 so I don't forget about it, but I'm kind of leaving it to the side until the end. Don't forget, right? Put a set of big parentheses before you do your lower bound, right? That negative, we don't want to lose track of how that negative can impact our answer. Okay. My area, I cleaned it up down to 32/3. Then I multiply by 1/4. And then I got to my average height. So let me scoot this down a bit more. All right, so that's part A. That's my average height. Okay, any questions there? So now part B, we're just going to take that height, that y value, put it back into the function and solve for x. And when you solve for x, just make sure that you're guaranteed that there's at least one solution between the interval. But sometimes you may end up with multiple solutions. Just make sure that you get multiple solutions, that you don't include the ones that's outside the interval. But then it's also possible where you have multiple solutions inside the interval. If that's the case, then you'll include all the answers, all the locations inside the interval. So I go back to my function, put 8/3 in for the y value. And so 8/3 equals 4 minus x squared. We don't want to use the antiderivative, okay? We want to go back to the original function. And we just want to find the order pair on that original function. So 8/3 replaces f of x. I'm just solving for x here, so subtract 4 from both sides. Divide both sides by -1. Take the square roots. Remember, square roots of an equation is going to result in a plus or minus. But if you test in your calculator, both 2/√3 and -2/√3 lands nicely between -2 and 2. So they're both valid locations for our c value. Okay, any questions? All right, I have a second theorem problem for us. Does anybody still need this? No, okay. I put the formula next to it so you guys can match it up. Okay, what did you guys do first?
Flip the upper and lower.
Yeah, the upper and lower bound doesn't quite match with what we want with our formula. So I'm going to flip the bounds, but we can always do that. Just have to make sure we adjust with pulling, changing that, adjusting with a negative as part of my expression. So now we just follow the rule, right? F of p of x, go ahead and replace every t value in your expression with my upper bound. So keep track of your exponents, and then multiply by the upper bound's derivative. So wherever I see the t, I just replace it with 2x cubed, but I want to make sure I keep track of what's inside and outside the parentheses. 2x cubed, I got to square everything inside that 2x cubed. So 2 gets squared, I multiply the exponents, so it becomes 2x to the 6th. 4x to the 6th. And then I'm going to multiply the 6x squared with negative 4x cubed, but now I'm multiplying bases, so I'm going to be adding exponents. So 2 plus 3 is 5. Remember, we can't cancel across addition and subtraction, so we can't cancel the x to the 5th and x to the 6th, right? Those are kind of stuck because the denominator has a 5 minus below. Okay. Questions? Good. All right, so if you know how to do this, then you should, all the second theorem problems should be pretty straightforward. All right, that's all I have. If you haven't finished your iReady test, make sure you complete that. I need that completed, or they need it completed completely by tomorrow end of day. Tomorrow we'll do use substitution, which is kind of undoing chain rule from first semester. Okay. All right, if you're on Teams, have a great day. I'll see you guys tomorrow.
Oh, it's like